Hello everyone, I'm Navin Sriram and I'm a Robotics Institute Summer Scholar for the year 2024 from the Indian Institute of Technology Madras. I'm here today to present my work conducted over the summer on the topic of learning to dress people while adapting to dynamic human motion using reinforcement learning. This work was conducted in collaboration with Yufei Wang, Professor David Hell from the iPad lab, and Professor Zachary Erickson from the RCHI lab. So moving on the topic of robot-assisted dressing, why is it necessary? Over 92% of residents in nursing home facilities and at home care patients require some form of assistance with dressing. Most prior works make innate assumptions such as availability of full haptic sensory data, some form of collaboration from the human, and they consider the human to be holding a fixed pose and being dressed with a fixed garment. Our approach is a non-collaborative approach for dressing a human with a moving pose with diverse garments using point clouds and deep reinforcement learning. So what makes this task so challenging? Traditional simulators excel in rigid body dynamics, but often struggle with the computational intensity and constraints needed for realistic cloth simulation. Currently, there is no known support for soft body manipulation with support for articulated humanoids at the same time. Added to this is the lack of benchmarking measures to validate the performance of the algorithm on moving hand poses. So coming on to reinforcement learning for dressing. So how do we utilize reinforcement learning for solving this challenging problem? So here's how we do it. So first we use reinforcement learning to reformulate the robot-assisted dressing problem as a partially observable Markov decision process. We additionally define the observation space as the raw point cloud of the scene which we get from the depth camera. This includes occlusions. We define the reward based on the dressing progress, and the action space is an SE3 delta transformation of the end effector with 3 degrees of freedom for the translation and 3 degrees of freedom for the rotation. So coming over to the training pipeline, we use the state-of-the-art soft actor critic algorithm for training all our policies. We use soft actor critic to first train a set of expert teacher policies that are trained only with small post variations. The actor and the critic are made up of the pointnet++ encoders to learn from feature-rich representations captured from the raw point cloud. We perform policy distillation to extract a single policy that can work over any given human pose. So what exactly is policy distillation? We can look at the dressing problem as a multitask learning problem where each task is dressing a particular pose. We decompose the pose into 27 sub-ranges and train expert teacher policies on these using SAC and extract a student policy using policy distillation. The policy distillation loss is formulated as a mix of behavior cloning loss measured through the Earth mover distance between the two distributions and the SAC RL loss. So now we have a short overlook over the shortcomings of the work we built on top of. So the work focuses on learning a policy using reinforcement learning, using segmented unoccluded point clouds to dress a human holding diverse fixed hand poses with different garments. The first main assumption this makes is unoccluded and segmented point clouds for the arm, claws, and the gripper, which are hard to extract, and they make an inherent assumption, which is a fixed arm pose during the entire duration of dressing, which may not be realistic considering real world dressing. So how can we extend on top of this work? So how can we adapt to moving arm motions? So we can train the policy on occluded unsegmented drop point clouds. Here we have no notion about the position of the arm among the scene. This is ideal for moving arms since we just want the capability to dress the arm at any position and we have no notion of history. So do we need to train all the teachers again with this changed environment? No. We can introduce this new world just at the stage of policy distillation and get a new policy out. So we tested this policy in real world dressing and it performed very poorly. So what could be the issue? So one inherent issue could be the sim to real gap and the lack of domain randomization. What if a training environment still does not resemble the real world flow scene, due to which it is not able to perform to its full capabilities in the real world? This gap can result from differences in physical properties, sensor noise, or actuator dynamics. So there are two possible gaps. So one is the absence of robot occlusion during the training environment. The four images on the left depict the training environment where you can clearly not see the robotic manipulator and the gripper, which cause significant occlusions on the human as well as the cloth. And during inference, we manually select a cropping point to give a portion of the scene point cloud and not the entire point cloud. And this selection is often done manually, leading to some errors. So we first need to validate if our claims are correct and if we actually need to fix this. So we evaluate the old policy on 270 variations after introducing the new features and we look at the performance. So in the world with the new occlusions and cropping, it gives a mean upper arm ratio of 0.12. The mean upper arm rest ratio is a measure of how much it has rest and the higher it is, the better. So in the world with occlusion and cropping, which is close to the real world, it's about 0.12. But in the original old world without any occlusions or cropping, it is 0.37. So we see about a 3-time decrease in the actual performance and the estimated performance. So we validate our claims that we actually have to reduce the sim to real gap. So how do we do this? One way to do this is by doing guided domain randomization during policy distillation. Naively doing domain randomization during training the teachers will often lead to no conversions and no learning at all. So we train the teachers, which are trained with no randomizations, and we train the students, which are trained with randomizations. So these randomizations include unsegmented occlusions, artificial robot occlusions, randomized point cloud cropping to include a part of the human torso, and this is randomized during every episode. And we have randomized point dropping, erosion, dilation, and adding random noise to the gripper position of the manipulator. So after addressing the sim to real gap by performing the added guided domain randomization during the policy distillation, we see a 2.5 times increase in performance of fixed time dressing, but the performance itself is still not good enough, looking at an absolute scale. So maybe figuring out the sim to real is not key to this, and the actual key is fine-tuning it in real world. So is it possible to do the fine-tuning in simulation? The answer is yes. So we first have to look at the SoftGem simulator, where we perform all of our training for all the policies. It is built on top of NVIDIA's Flex simulator, which models flows accurately in a particle in position based dynamical system. So we make a new end-to-end simulator which has a fully articulated 56 degrees of freedom humanoid with independent control on each joint with joint torque control. And we use this simulator environment for training all our policies and fine-tuning it in real world. So moving on to the real world fine-tuning setup. So everything in reinforcement learning happens in small steps for episodes where you roll out the policy and then undo whatever you did and reset the state and you roll out the policy again. And you continue this until the policy learns something useful. So what does this reset mean in the real world? For our task, the reset is basically undressing the robot after dressing it. So we use a delay-aware controller for undressing the robot by constantly monitoring and logging the actuator delays. We use joint velocity control for performing the dressing to increase speed and having smoother commands. One successful episode is one complete policy rollout. When the Sawyer goes too close to the mount, it triggers a reset state to undress the arm. Here is a short overview of how it happens, a time-lapse video of 4 dressing and undressing maneuvers. So in the previous video, you would have noticed that the Viper or the arm which is supposed to imitate the human arm, the small black arm, was stationary, while the red Sawyer arm, which is dressing, was moving, was dressing and undressing. So for real world fine tuning, we'll have to dress the arm when it's constantly moving. So this requires synchronizing between both the arms, where the human arm performed some random motion primitive and the Sawyer arm will be dressing it. So here's an example of how we do this. Use a simple go-to-goal controller with a finite state machine to make this possible. I'll be providing more details about the finite state machines in the upcoming slides. But this is a small demo of rolling out about 10 episodes on the real world RL setup. So you could see the Viper arm executing predefined motion primitives and the Sawyer arm rolling out its policy, dressing it, and then undressing itself, and then starting over. So this is the rollout. It reaches too close to the point, so it triggers the safety guarantees and starts undressing, and this also starts moving back at the same time, and this will start dressing again. So we have a perfect synchronization between the two arms to learn in real time. For achieving the perfect synchronization between both arms, when the Sawyer starts to roll out, the smaller arm starts moving, and whenever the Sawyer arm comes close to some obstacle, it resets, and the smaller arm resets at the same time. For achieving the synchronization, it is necessary to operate the Sawyer in a finite state machine framework. We use three states: the forward, reset, reverse, and another state called error. So we also have safety guarantees which trigger the switching between states. So the first safety guarantee is collision avoidance. This is a robust module which takes as input the joint poses of the Viper and computes an approximation of the arm surface with KD trees and regularly queries for the nearest neighbor and nearest distance at all points of time. And for the second safety guarantee is the garments getting stuck. During dressing and undressing, the cloth is pretty flimsy and it might get stuck near the boxy edges of the moving arm. So any kind of close touching would put extra effort on the Sawyer robot's gripper, and this would be shown as a sudden jump in the effort. We monitor the efforts of the gripper of Sawyer at every instant to notice such jumps in magnitude, and whenever we notice a breach in both of the safety guarantees, we trigger a reset, which immediately starts the undressing maneuver, and we reset the episode. So this gives rise to the final pipeline, where we use the old existing architecture with guided domain randomization to achieve good policies, but not optimal policies, and we further fine-tune and refine them with real-time RL, and then we benchmark it on the moving arm setup and perform validation studies on human participants. So conclusions and future work. So we have improved the performance of the existing work by 3.5 times while working on occluded point clouds. Occluded point clouds are key to solving the problem of tracking and adapting to human arm motions, since there's no notion of arm position and there's no history carried on except from the PMDP formulation itself. We have developed two new pathways to which the policy could be refined further through hardware and software. The new simulator pipeline could be used to test out potentially better policy and queue function architectures, utilizing history-based methods by conditioning the networks of the scene flow, where we compute the optical flow over the entire point clouds, where we can track movements and the magnitude of the movements very efficiently.